Welcome back, everyone, to another deep dive. And this time, we're looking at this paper that I think you're really going to be interested in dealing with continual learning. And how do we make sure that those models are robust against adversarial attacks?
Yeah, this is a really interesting area because obviously there's a ton of work on adversarial robustness in the kind of standard deep learning setting. But, when you start thinking about continual learning where, models are constantly evolving and you're getting new data, it just adds this whole other layer of complexity to the problem.
Right. And so this paper kind of sets the stage by saying, okay, we're going to look at robust multi-class classification in a continual learning setting. So basically, you've got these models that need to learn new classes without forgetting the old ones, and they got to do it all while fending off these attacks.
Yeah, and so the authors really zeroed in on this problem of catastrophic forgetting of robustness. So, even if a model learns to be robust on one task, as it continues to learn new tasks in a continual learning setting, it tends to kind of forget that previously learned robustness. And so this is a really big problem if we want to actually deploy these models in the real world.
So to tackle this, they present this method called RCLTB, Robust Continual Learning with Task-Aware Boundary Augmentation. And I think maybe before we jump into all the specifics, can you give us a high-level overview of how this approach works?
Sure, yeah. So RCLT beta kind of builds upon this idea of adversarial training, right? Where you're essentially trying to expose the model to adversarial examples during training to make it more robust. But the kind of key innovation here is this idea of task-aware boundary augmentation, or TBO. And essentially what this method does is it's a data augmentation technique where you are strategically augmenting the training data with examples that lie near the decision boundaries of the model.
Okay, so instead of just kind of randomly adding noise or perturbations, they're really thinking carefully about where those data points are coming from. What's the rationale behind focusing specifically on these boundary examples?
Yeah, so the idea is that, these boundary examples kind of represent the areas where the model is most uncertain. And so by kind of manipulating those examples and forcing the model to kind of pay attention to them, you can actually improve the model's ability to distinguish between different classes, even under adversarial pressure.
So it's forcing the model to be more discerning and less easily fooled by this adversarial noise. But how does this actually work in the context of continual learning? How do they prevent the model from forgetting that robustness on previous tasks?
Yeah, so that's where the task-aware part comes in. So TABA carefully selects these boundary examples from both the old tasks and the new tasks, and it interpolates them in a specific way. So it actually uses a technique that's inspired by mix-up, but there's a crucial difference.
Mix up. So that's where you're blending two images together, right? So they're doing something similar, but with these boundary examples.
Exactly. Yeah. So with mix-up, you're kind of just randomly blending these images together. But with TABA, the weights that are used to blend these images are carefully constrained to ensure that the resulting augmented data points remain close to those decision boundaries.
So it's not just about randomly mixing data. It's about very deliberately creating these new examples that target the model's vulnerabilities and doing it in a way that preserves that knowledge from the previous tasks. It's a really clever approach.
Yeah, and so the authors really thought carefully about, how to combine these ideas of adversarial robustness and continual learning in a way that kind of works well together.
Now, they use a specific type of adversarial attack in their work. Can you remind us what that was and why they chose it?
Yeah, so they use projected gradient descent, or PGD, and they use a maximum perturbation magnitude of 18 to 55. So PGD is a pretty common attack method that's used in adversarial robustness research, and it essentially tries to find, the direction in which to perturb the input data to maximize the model's error.
So they're training against this fairly strong and commonly used attack method, which makes sense, but I'm guessing it's not enough to just train with these adversarial examples and then assume that the model will be robust in all situations.
Right. Yeah, the real challenge is to see, does this actually work in a continual learning scenario? And that's where the experimental setup and the evaluation metrics become really important.
Okay, let's move on to that. Now, what data sets and models did they use to put this RCL TABA to the test?
Right. So they use CIFAR-10 and CIFAR-100, which are two pretty common image classification data sets. And they use ResNet-18 as their kind of backbone model.
Okay, so pretty standard data sets and model architecture, so
Right.
that makes sense. And what about the evaluation metrics? How do they actually measure robustness?
Yeah, so they use three key metrics. They look at standard accuracy, which is just, how well does the model perform on clean data. They look at robust accuracy under PGD attacks. So, how well does the model hold up against the specific attack that it was trained on? And then they also look at robust accuracy under auto attack, which is a more powerful ensemble attack that kind of tries to find even stronger adversarial examples.
Hmm. So they're really making sure that it can withstand these attacks,
Sure.
both the specific one it was trained on and then this more challenging ensemble attack that gives a much more complete picture of how robust the model is.
Right. And so, this is really important to kind of get a sense of, okay, how well does this method actually work?
Okay, so they've got this really solid experimental setup. What were the results? Did RCL-TBA actually deliver on this promise of robust continual learning?
Yeah, the results were actually really impressive. So, RCL-TABA consistently outperformed other approaches in maintaining both standard and robust accuracy across a variety of continual learning scenarios. And so it really showed this, significant ability to retain its robustness on previous tasks while still effectively learning new ones.
That's fantastic. It sounds like they've achieved a pretty significant breakthrough here in robust continual learning. Can you tell us a bit more about what those other approaches were and how they compared?
Yeah, so they compared RCL-TABA against a number of different methods. So, for example, they compared it against ICARL, which is a pretty classic continual learning method.
Hmm.
And, ICARL showed okay performance on standard accuracy, but it really kind of fell apart when it came to robustness against adversarial attacks.
So it's not enough to just have a model that can learn continuously. It also needs to be resilient to these attacks. Did they look at any other approaches that specifically targeted robustness?
Yeah, so they also looked at RCL, which is essentially just combining adversarial training with ICARL. And, this showed some improvement over ICARL in terms of robustness, but it still kind of suffered from this forgetting of robustness as new tasks were introduced.
But just adding adversarial training on top of a continual learning method isn't enough.
Yeah.
You need something more sophisticated to handle this dynamic nature of continual learning. Did they compare it against any other data augmentation techniques?
Yeah, so they compared it against boundary exemplar, which is a method that specifically focuses on boundary data for continual learning. And while this showed some promise, it still kind of fell short of RCL-TABA's performance. And they also compared it to Mixup, which is a more general data augmentation technique. And Mixup actually kind of struggled to maintain good standard accuracy in the continual learning setting.
It's fascinating how each of these comparisons really highlights a different aspect of this problem. It really shows the unique challenges of achieving robustness in this continual learning environment. Did the authors give any insights into why RCL-TABA was so effective?
Yeah, so they actually did a pretty detailed ablation study where they kind of systematically removed different components of RCL-TBA to see, how much each component contributed to the overall performance. And, one interesting finding was that if you remove the task-aware component of TABA, the model's ability to retain robustness on previous tasks significantly decreased.
So it's not enough to just augment the data you need to do it in a way that is sensitive to the order in which the model learns tasks. So that's a really valuable insight. It also speaks to the importance of ablation studies in really understanding what drives a method's performance. Did they have anything to say about limitations of their approach or areas for future research?
Yeah, so while RCL-TIBA shows really promising results, the authors acknowledge that it primarily focuses on image classification, and so one area for future research is to see how these ideas can be applied to other domains like natural language processing or time series data, where the nature of adversarial attacks and the challenges of continual learning might be quite different.
That's an excellent point. It's one thing to achieve robustness in this nice controlled image classification setting, but it's another thing entirely to do it in these more complex domains where the data and the attacks can be much more varied. Did they have any other thoughts on future directions?
Yeah, so they also suggest looking into how TABA could be adapted to handle more dynamic continual learning scenarios where the task boundaries might be blurry or the data distribution might change over time. And so this is a really interesting direction for future research to kind of make these models even more adaptable and resilient.
That's great that they're already thinking about those future directions. It shows that they're aware of the limitations, and they're actively looking for ways to push those boundaries even further. This paper really tackles a critical issue in continual learning, and it sounds like it offers some genuinely promising solutions. Before we wrap up, any final thoughts you'd like to share with our listener, who I know is deeply involved in this field?
I think the main takeaway here, especially for our listener and their expertise, is this idea that RCL-TABA is giving us a really solid foundation for building these robust continual learning systems. it really shows how important it is to focus on those decision boundaries and tailor your data augmentation to this continual learning setting.
Yeah, absolutely. And the ablation study was really insightful in showing how each piece of TABA contributes to both the standard and robust accuracy.
It's clear that you can't just take existing techniques like adversarial training or mix-up and just kind of slap them together.
Yeah.
You really need methods that are built for the specific challenges of continual learning. And RCL TABA seems like a really promising step in that direction. What's exciting to me is that this could really open up a lot of new research directions. The authors themselves have pointed out some promising avenues like adapting this to other domains or to even more dynamic continual learning scenarios.
That's a great point. And
Yeah.
and as we see these continual learning models being used more and more in the real world, that need for robustness is only going to become more and more important.
Mhm.
Think about something like a self-driving car that needs to constantly learn new traffic patterns, but also be resilient to attacks that could mislead its perception.
Absolutely. Or you could even think about personalized medicine, where you have a model that's adapting to a patient's changing health data, but it needs to be robust to any noise or errors in that data.
The possibilities are really endless, and I think this research really drives home the point that robustness isn't just an afterthought. It's really a fundamental requirement if we want to build these continual learning systems that we can actually trust and rely on.
I think that's a great way to put it. This deep dive has really shed light on a crucial area of research that's going to be so important for the future of machine learning. And I'm sure our listener, with their expertise, will find this really valuable as they continue their own work.
Well, thank you so much for joining us on this deep dive. We hope you found it informative and thought-provoking. Until next time, keep pushing the boundaries of knowledge.